Welcome back to this course on nanostructured materials, synthesis, properties, self assembly and applications. So, we are in the module 4 and today is the second lecture of module 4 and it is also the second lecture on photocatalysis. So, in the previous lecture we discussed the preliminaries and the basics of photocatalysis, that is you are catalyzing a reaction in the presence of light and a catalyst is being used, and a catalyst, the definition of a catalyst is one which is participating in a reaction and lowering the activation energy of the reaction and hence and is also regenerated at the end of the reaction. Now, this is a definition for a general catalyst. A photocatalyst has these properties in the presence of light. So, it works in the presence of light and light can be of different frequencies, and the frequencies of light which are of interest is mainly in the visible and in the ultraviolet, because that is the light or the which we want to use from the solar radiation, and hence the region of the electromagnetic spectrum that is of interest in photocatalysis is the visible region and the ultraviolet region. So, continuing our lecture on photocatalysis, today we will be discussing specially the photocatalysis or splitting of water in the presence of light, how materials can catalyze this splitting of water to give hydrogen and oxygen, which is the photocatalytic process in the presence of sunlight. Now, as you know, the fuel is a real problem for the future. You have coal based fuel, you have natural gas, you have hydroelectricity. From different sources you can generate power, but one of the future sources of power is considered to be hydrogen, and people want to know how to produce hydrogen for different purposes, for local use and for use as a fuel for large industries, etc. So, among the various methods for hydrogen production, thermochemical routes are there, electrolytic routes are there, photolytic routes of hydrogen formation are there. Then there are biochemical pathways and also chemical reformation of naphtha, which is obtained naturally. So, you can have several methods by which you can produce hydrogen. The process with which we are interested in this part of our course is the electrolytic generation of hydrogen or the photolytic generation of hydrogen. So, this is a photocatalytic process, this is photoelectrochemical process by which you can generate hydrogen. So, what is the photoelectrolysis of water? Now, the discovery of photoelectrolysis of water directly giving oxygen at a titanium dioxide electrode and hydrogen at a platinum electrode was of tremendous interest and is a major breakthrough in science, and this was attributed to Fukushima and Honda, and they showed this reaction sometime. It is reported in the paper Chemical Reviews in 1972, and so it is a long time that people have been working on titanium dioxide as the material at the electrode where oxygen is generated, and you have another electrode which is platinum where hydrogen is generated, and these two electrodes are in aqueous medium. So, from water you are generating oxygen and hydrogen. So, this is basically water splitting, and you are doing water splitting in a electrochemical cell. So, this is photoelectrochemical splitting of water, or we can call it photoelectrolysis of water. And Fukushima and Honda's work is a major breakthrough using titanium dioxide as one of the photocatalysts, and titanium dioxide has a band gap of around 3.1 electron volt, and this is a semiconductor, and as we will see that the semiconductor band gap for photocatalyst is very important for water splitting, and what kind of band gaps are important, that we will study in the near future. Just photocatalysis, that is not splitting of water, but catalysis of certain reaction in the presence of light by titanium dioxide, however, has been reported much earlier than 1972, and it was reported in 1955 by Markham. So, photocatalysis was studied much earlier, although photoelectrochemical synthesis of oxygen and hydrogen from water, which is water splitting reaction, was first shown by Fujishima and Honda, and is a remarkable breakthrough in science. So, the electrode of Fujishima and Honda. So, this is the work that I was referring to. It is published in Nature in 1972, and you have this electrochemical cell. So, what is there in an electrochemical cell? You normally have two electrodes. So, here also you have two electrodes. You have this cathode where you have these electrons which are going to the external circuit, and this cathode is of material which is titanium dioxide with a band gap of around 3.1 electron volts. So, this is the valence band of titanium dioxide, this is the conduction band of titanium dioxide, and this is an N type semiconductor, and this is the photoelectrode. What you mean by a photoelectrode is when you want to do electrochemical reaction in the presence of light, then you have electrodes on which light has to shine. So, that electrode, that particular electrode where out of the two electrodes you have one electrode where you shine light, and that is called the photoelectrode. So, the photoelectrode here is titanium dioxide, it is a N type semiconductor material, and as shown this is the band gap, and the other electrode is the platinum electrode. So, in this electrode when you shine light, which is the light should have a wavelength less than 415 nanometers, because then only it will have energy more than 3.1 electron volts, and if this light has energy more than the band gap, then only it can produce electrons and holes. That means, electron can be transferred from the valence band to the conduction band only when this light has energy which is more than the band gap, which is around 3.1 electron volts, and for that the light has to have a wavelength which is lambda less than 450 nanometers. So, that is in the ultraviolet radiation, it is in the UV region of the electromagnetic spectrum, and so when this light falls on this electrode which is having titanium dioxide, electrons are produced in the conduction band and holes remain, because whenever electron goes away you generate a hole in that band. So, an electron comes here and a hole is generated here, together this electron and hole is called an exciton, and then this electron then goes out of into the external circuit, and you generate this hole which is generated reacts with the water or the aqueous solution which is the electrolyte, and the reaction of this hole with this water will generate oxygen. So, at this electrode which is the cathode, oxygen is generated, oxygen gas comes out and electrons are pushed in the external circuit. On the anode which is the platinum counter electrode, electrons come here and these electrons act on water which is the aqueous solution, and then hydrogen is generated. So, you are oxidizing here, you are reducing here the material, and this hole is oxidizing water to oxygen, and here you are reducing the protons from the aqueous solution into hydrogen. So, the hydrogen is generated in the anode and the oxygen is generated in the cathode. So, basically from one water molecule plus one water molecule. So, 2 water molecules are getting used in this reaction and 1 mole of oxygen and 1 mole of hydrogen is being produced. So, the overall reaction you have 2 moles of water giving you 1 mole of hydrogen and 1 mole of oxygen, right. So, this way you have to balance this equation, of course, when you write 2 H2O giving you H2 plus O2. So, you have to balance that equation and you will have 2 moles of H2 in this process. Now, if you so this is a typical electrochemical cell which was used by Fujishima and Honda to show that titanium dioxide is a semiconductor which can act as a photocatalyst and can split water, and this semiconductor is used as a photoelectrode. Normally, the semiconductor is coated on another metal which acts as a foil behind it to give its mechanical strength and conductivity, but the actual reaction of light is with the semiconductor to generate the electrons and the holes. So, that is the photocathode. Now, what is the challenges in this decomposition of water? So, as I said that the protons H plus ions react at the anode with the electrons which are coming from the external circuit and produce hydrogen at the anode, and on the other electrode you have got oxygen, and this oxygen plus will take 4 electrons plus protons to give water. So, in the other electrode actually it is this reaction, the reverse reaction, H2O giving you oxygen, the reverse way, and the difference of the potential required for this, because this is a standard hydrogen potential. So, that is kept at 0 volts, and this is the potential you require for this reaction. Since you want the reverse reaction, so this will be negative, but anyway the energy difference that you require is around 1.23 volts. So, the minimum band gap, because so much energy is required for these, the sum of these two reactions requires 1.23 volts. Hence, the band gap should be of the semiconductor should be at least 1.23 electron volts. So, as TiO2 has a band gap of around 3 electron volts or so. So, that takes care of the 1.23 electron volts which is minimum for water splitting. So, this 1.23 electron volt which you get by subtracting this from this, you subtract the cathode minus anode, and this is you will get the difference is 1.23 electron volt, and this is the minimum energy you require, and this minimum energy means when you have photo generated electrons and holes, that is when light shines on the photo cathode, electrons and holes will be generated, then the band gap between them should be at least 1.23 electron volts. The other point is, so this is the first key point, that the band gap should be minimum 1.23 electron volt for water splitting. The second point is the charge must transfer from the surface of the semiconductor very quickly. So, the charge means you have got electrons and holes in the semiconductor, and this electron and hole are required at separate parts of the material for reaction, and they must not recombine, otherwise you do not use the electron and the hole. So, charge transfer must be fast to prevent what is called photocorrosion, and shift of the band edges result in loss of photon energy. So, the band edge shifting can lead to loss in photon energy, right. So, these are some of the points which are important for the photoelectrochemical splitting of water. This is the same reaction shown in a different way, where this is a semiconductor and you shine light, this is a valence band, this is a conduction band, and this is the other electrode which is normally the metal electrode. This is a semiconductor like titanium dioxide or any semiconductor which has got appropriate band gap, that means more than 1.23 electron volt, and also the band edges, that is the conduction band edge and the valence band edge should be in such a manner that electron can be transferred to the conduction band of the H2, the water and H plus couple. So, this for this reaction the upper band or the conduction band is here and the valence band can be thought of as here, and so the difference is what we discussed earlier, 1.23 electron volt. Now, this conduction band of the semiconductor is higher than the conduction band of the water couple, and so electrons can be transferred here, and the holes have are the valence band where the holes are present in the semiconductor are lower than the band edge of the valence band of the water hydrogen couple, and hence holes can be transferred here. So, we say that electrons can be transferred from the conduction band of TiO2 to the conduction band of the hydrogen, and holes can be transferred in this way, right. And so, the overall reaction written here in aqueous medium is basically 2 water molecules give you 2 moles of hydrogen and oxygen. So, this is the water splitting reaction in the presence of light, and as we said, it is not possible to use semiconductors whose band gap is less than 1.23 volt. For higher than 1.23 volt, all semiconductors which have higher than 1.23 volts, there are additional points which one must consider, and that additional point is that the valence band is lower than the valence band of the couple, and the conduction band of the semiconductor is much higher than which means more negative potential. As you are going up, you are more negative potential and it should be much more negative potential than the conduction band of the couple, which is the unsubstituted system. Now, how to understand this process or how to do an experiment to find out hydrogen and oxygen are being generated. So, you can use the catalyst which is titania, and you irradiate with light. So, you shine light of a particular frequency which is h nu, and h nu is can be in the region of the ultraviolet or the visible, and hydrogen and oxygen are detected through a gas chromatograph or through mass spectrometry, and this is the process what is happening which we discussed, that electrons and holes are produced when light falls on the semiconductor particle, and the electron moves towards a direction where it can reduce the protons to hydrogen, and the holes have to migrate to the surface where it can oxidize H2O to oxygen. So, the electrons produce the hydrogen and the holes produce the oxygen, and this is the water splitting reaction. And this band diagram we already discussed, where the valence band is here and the conduction band is here, and the H plus H2 and O2 H2O couple is shown here as 1.23 electron volt, and so you need higher energy than that, and this is on a scale taken with normal hydrogen electrode, and all the holes will be in the valence band, which then react with water to give you oxygen, and all the electrons can be pushed to the conduction band and they react with H plus to give hydrogen. And the rate at which electrons can react, this migration is around 10 minus 3 seconds. So, it is in milliseconds, whereas holes it is much, it takes much small time, that is 10 to the power minus 8 seconds. So, there is a difference in the electron and hole transport, and these points are important while planning or designing new photocatalytic systems. Now, the conditions for photoelectrocatalysis or photoelectrolysis are that the band edges of the electrode must overlap with the acceptor and donor states of water decomposition reaction, which we already discussed, and thus the electrode should have at least a band gap of 1.23 volt, which is the reversible thermodynamic decomposition potential of water. This also we discussed earlier, and all semiconductors need not be able to split water unless they have this condition. The other important condition is the charge transfer from the surface of the semiconductor must be very fast to prevent recombination of the electrons and holes and to prevent photocorrosion. So, the photocorrosion will lead to shift of the band edges and result in loss of photon energy. So, these are some of the conditions for having efficient splitting of water through photoelectrochemical processes. Now, what one can do is to get better and better photocatalysts is to modify, for example, the surface or use sensitizers. You can do several things. So, what are these modifications one can do to improve the efficiency of the photocatalyst? So, one of the methods is dye sensitization. So, dye can be normally organic dye. So, these are organic molecules which can help in electron transfer. So, that is used in certain cases where you can sensitize a semiconductor using a dye, which is basically an organic molecule. Then you can do surface modification of the semiconductor to improve its stability. You can combine two semiconductors. So, they form multi-layered systems. Then you can dope wide band gap semiconductors like TiO2 by nitrogen, carbon and sulfur. So, you will have states within the band gaps, and those states can then act as which can be at lower level than the conduction band of the semiconductor and can be useful in transfer of electrons. So, doping, it can also help in the holes, presence of holes. So, depending on what kind of dopant you use, you can change the nature of the electron hole stability in wide band gap semiconductors by doping with atoms like nitrogen, carbon and sulfur. Now, several semiconductors with metal 3D valence band can be used instead of oxygen 2p contribution. You can use sulfur, for example. So, you will have a sulfide band which is overlapping with the metal band. So, there can be other than metal oxides as semiconductors, and of course, depends whether you want they should have band gap more than 1.23. Normally, the band gap will decrease when you change an oxide to a sulfide. You can also sensitize the photocatalyst by doping. So, several modifications one can do, and some of these lead to enhancement of very high enhancement in the photocatalytic efficiency of splitting of water. So, the mechanism of the recombination reduction by metal doping. So, you are trying to dope metals. So, what happens? The metallic promoter attracts electrons from TiO2 conduction band. So, now in a typical experiment, you generate electrons in the conduction band and holes in the valence band when you shine light. So, you have electron hole pair generation, which is called, and these electron hole pairs are called excitons, and the opposite process of electron combining with holes is the electron hole pair recombination, and this process is avoidable. This is not good for the photocatalyst. So, you want to avoid this electron hole pair recombination. Now, when you have a metal as a promoter, that means, if you add metal dope metals, these metal bands can attract electrons from the titanium dioxide conduction band. So, these electrons can be taken up by the metal and the metal can maintain these electrons. So, you are removing these electrons from the site where from it can recombine with the holes, and that this process of recombination can be slowed down when you dope metals, because the metal are acting as electron traps. So, selecting appropriate systems as photocatalysts for water splitting reaction. How do you go about that? You can choose substituted systems, like as we just showed, metal doped systems, or even bare semiconductors which favor dissolution. They may undergo preferential photocorrosion and hence cannot be exploited for photocatalytic pathway. Now, if so, what we said is that if you can add metals which can take up electrons, then the recombination process can be slowed down, and this is helping the cause of photoelectrochemical splitting of water. However, if you have systems which favor dissolution, then only preferential photocorrosion will occur and cannot be exploited for the photochemical splitting of water. And this is an example of zinc oxide, where it cannot be used as for photo electrochemical splitting of water due to its preferential photocorrosion. Now, low ionic character, we discussed about ionic character of bonds in the previous lecture, where suppose you have a metal oxide, then the metal oxygen bond can be ionic or covalent or partially ionic, and if it is partially ionic, what is the polarity of the bond can be calculated from the difference of the electronegativity of the metal and oxygen. So, ionic character can be calculated, and higher the ionic character, the higher is the band gap, and if low ionic character is there, then the band gap will be very low, and then you will not be able to use that for splitting of water, because lower than 1.23 volts will now allow you to split water. So, hence if you want to use more than 1.23 volts, then the lower end of the visible region is not possible. So, you will have to use the higher end of the visible region towards the ultraviolet to have materials which have higher band gap than 1.23 volts. So, low ionic character which will give you low band gaps than 1.23 volts will not be suitable for direct water splitting reaction. Now, if you want to use visible light, then only one of the photoredox reactions in water splitting may be preferentially promoted. That means, either the reaction at the cathode or the reaction at the anode may be promoted depending on where is your conduction band edge and where is your valence band edge. But what you need for typical photochemical splitting of water is both the reactions should be promoted. The reaction at the cathode, which is generation of oxygen, and the reaction at the anode, which is generation of hydrogen, both have to be equivalently efficient, then only you will have a good photochemical splitting of water. So, many catalysts may not do both of them, and then it can be only used to do one part of the reaction, and that is what is mentioned here, that sometimes using visible light, when you do not have energy more than 1.23 volts, you can still do some photo reaction, photocatalytic reaction, but here you may not have equivalent amount of oxygen and hydrogen, because one of the processes is preferred more. So, you may have more of oxygen and much less of hydrogen being produced, or much more hydrogen and much less oxygen. So, it is not a typical photochemical splitting of water. Now, systems which have ionic bond character of around 20 to 30% with appropriate or the right kind of position of the valence band edge and the conduction band edge, it should be appropriately placed with respect to the levels which are of for the water and oxygen couple. And so, if you have around 20 to 30% bond character, then it is possible to have water splitting reaction when appropriately the conduction and the valence band edges are placed with your water oxygen and water hydrogen couples. Now, how do you engineer the semiconductor electronic structure? So, you are using semiconductors as the photocatalyst. Now, how do you engineer them? You have to take into account certain points, like one of the points is of stability, because you want the photocatalyst to be used and reused several cycles, several times. So, it should work without deterioration of the stability. So, that is one of the important points. Then how to increase charge transfer processes at the interface, that is at the interface where the semiconductor is meeting your junction, which is water. How to improve the efficiency of this photo generation or charge transfer across the photocatalyst, and developing nano size systems. So, how to develop nano structured materials which may help in the efficiency of the photochemical splitting of water. So, if you look at this pie chart, it shows different kinds of materials and on which work is being carried out and investigations have been carried out, and people are studying them for photocatalytic hydrogen production. So, the amount of work that people are doing based on titanium dioxide is immense. So, the whole world is working on titanium dioxide, large amount, actually nearly 36% of the work on photocatalysis is based only on one material, only on one semiconductor, and that is titanium dioxide, and that is the brown colored part, and that is 36.2%. Whereas, other materials have also been used as a photocatalyst, other semiconductors like oxysulfides, which is around 19%, oxynitrides much less 5%, then non-titania based oxides. So, there can be other oxides which have been used for as a photocatalyst, say tantalum pentoxide, niobium pentoxide or many other materials, and they have a share of around 11%. So, people have used non semiconductors also like insulators or metals, but the amount of literature on that is much less. So, from this pie chart, one thing is clear, that one compound which is titanium dioxide is having more importance, nearly more than 1/3 of the work done among all hundreds and thousands of compounds which have been tried to be seen as a photocatalyst for splitting of water. So, titanium dioxide holds great promise in the market, and it is for two reasons, because it has a good reasonably good efficiency, is easily available and is also economical and non toxic. So, for all those reasons, titanium dioxide is a very important material for photochemical splitting of water. Now, the advantages of semiconductor nanoparticles, that means, if you use nanoparticles instead of bulk particles. So, what is the difference? You are going to use a semiconductor, but now you want to use a semiconductor whose particle size or grain size is much smaller than bulk semiconductors. So, the particle size can be 30, 40, 50 nanometers, and so what is the advantage that you gain in the photocatalytic splitting of water using these semiconductor nanoparticles? One, you will have very high surface area, and for any catalytic reaction surface area is very important, because the larger the surface area, you have more catalytic sites, and so the reaction is much faster. Second is the morphology. In nanostructures, you can tune the morphology, you can make spheres, you can make wires, you can make plates, and so the morphology will affect the efficiency of the photocatalysis of water. So, if it has high surface area, obviously you will have lot of surface states, and this will give rise to efficiency of this photocatalysis. Then you can have wide band gap semiconductors, because as you know, when you change the size of a particle from a bulk particle, if you make it into a nanoparticle, then the band gap increases, and the band gap is increasing means you are making something a wide band. So, from a narrow band you are changing it to a wide band when you are making the size of the particle small. The same semiconductor can have different band gaps depending on the size of the particles. So, if you have a 1 micron size particle, or if you have 40-50 nanometer size particle of TiO2, they will have different band gaps, and the band gap is larger for the smaller particle. So, you can make wide band gap of a small or narrow band gap material. Then the position of the valence band and the conduction band edges will also change as you change the size of the particles. So, because of all of these properties, it is advantageous to use semiconductor nanoparticles for photochemical water splitting reactions. So, nanocrystalline materials typically titanium dioxide we discussed a lot. The other materials which are very popular are zinc oxide, tin dioxide, it should be SNO2, and niobium pentoxide, or chalcogenides like cadmium selenide, etc., with high internal surface area can be used with a dye. So, if you adsorb a dye, is an organic compound as a monolayer, then the entire lot can be retained on a given area of the electrode, so as to absorb the entire incident light. So, if you have nanocrystalline materials, then the dye can be adsorbed in such a way that you can absorb the entire incident light. Also, since the particle size is small, there is no significant local electric field due to the particle, and hence the photo response, that means the response of the material when you apply the light. So, when photons fall on that material, it will mainly be, the response will be mainly due to charge transfer with the redox couple, and there will be no effect of the particle's own or local electric field, because the size of the particle is very small. So, the photo response will then mainly be contributed by the charge transfer with the redox couple. Two essential factors which contribute to the voltage developed, because when you shine light on a semiconductor, you will have a voltage which is developed, and there are two important factors. One is that the contact between the nanocrystalline oxide and the back contact, that is, you have to attach a wire to connect the voltage, that is from through which the current will flow. So, this contact is called the back contact, which is having an interface with your semiconductor. So, this back contact of the material as well as the Fermi level shift of the semiconductor as a result of electron injection. So, when you have electrons from the semiconductor which will go into the contact to participate in the external circuit, then there is a Fermi level shift, and these two factors are important. How this shift in the Fermi level of the semiconductor affects the overall photochemical efficiency, that is one important thing. And the other thing is the interface between the back contact and the nanocrystalline material, which is maybe an oxide or a sulphide, that also is very important. The as we said that the nanocrystalline state will increase your band gap. So, increases the band gap compared to the bulk, material, and this increase in band gap will facilitate both oxidation and reduction reactions, which may not be possible on bulk semiconductors. So, if you have semiconductors which have micron sized particles, those are called bulk semiconductors, and so when you have that bulk semiconductor will have some band gap, and when you are making the nanoparticles of that bulk semiconductor, then it will have a much larger band gap, and which may promote the oxidation reduction reactions. It may be because the bulk band gap was much small, and now the band gap which has increased is appropriate for doing such oxidation reduction reactions. Now, if you look into a particular example of say a single crystal of anatase. Anatase is one of the forms of titanium dioxide, and this is the form which is used a lot for photocatalysis. And if you look at the response of this a single crystal. So, take one single crystal, not a polycrystalline material, and then compare it with a film of titanium dioxide. So, one is a single crystal, the other is a porous TiO2 film, and it is sensitized by a dye. Now, this dye is a organometallic compound, it has a metal which is ruthenium and with some ligands, and there are two ligands which is a bipyridyl dicarboxylate ligand, and there are two thiocyanate ligands. So, this thiocyanate is a monodentate ligand and this bipyridyl is a bidentate ligand. So, ruthenium is L2 SCN2 is like an octahedral molecule, and it behaves like a dye, and this is a common dye which is used. Now, when you use this dye with the crystal single crystal, or you use this dye with the mesoporous film and calculate or measure the current conversion efficiency. So, there is a term which is called IPCE, which is the incident photon to current conversion efficiency IPCE, and this value should be high. Now, this value is 0.13% at a particular wavelength, which is 530 nanometers, which is the wavelength which this dye absorbs. So, this dye is actually like a sensitizer. So, the single crystal anatase and the mesoporous TiO2 film is doped with this dye, this ruthenium complex. This dye absorbs this radiation at 530 nanometers and helps in the oxidation reduction reactions of the semiconductor, using the semiconductor. So, without when you do not have a single crystal, when you have the mesoporous film which has very large surface area, then the IPCE, that is the efficiency, photon light to current transfer efficiency, increases drastically. 0.13% was the efficiency of the single crystal, and it became 88% when you take the mesoporous film. So, that is an increase of nearly 600 to 700 times. And what has been changed? The only thing you have changed is, instead of using a single crystal, you are now using a mesoporous titania film. The dye is the same, the incident light is the same, it is 530 nanometers, but the efficiency has increased to 88% from 0.13%. So, this dramatic increase in the efficiency can be connected to the surface area of the mesoporous titania film. Now, based on these energy levels, which is the position of the band of different kind of semiconductors, you can find out which semiconductor will be useful for hydrogen generation and which semiconductor will be useful for oxygen generation. Now, this is the scale is given with respect to normal hydrogen electrode, and with normal hydrogen electrode you see that 1 gram of hydrogen is equal to 0.05 gram of oxygen. So, this is the scale is given with respect to normal hydrogen electrode, and with normal hydrogen electrode you see that 1 gram of hydrogen is equal to 0.05 gram of oxygen. So, if you have a band edge which is higher than the band edge of the other material, then it says that this will be better for hydrogen generation, but will be poorer for oxygen generation, because the valence band is higher than this. So, if the valence band is lower, that would help in oxygen generation. If the conduction band is higher, it would help in hydrogen generation. So, this is given in the scale such that the water oxygen energy level is shown here, and all these semiconductors, these are oxides. You can find out from this plot which one you will use to choose a material for semiconductor catalyst for hydrogen generation or for oxygen generation. And so, as I said, the lower the conduction band, better it is for oxygen generation catalyst, higher the lower the valence band, better is the oxygen generation, higher the conduction band, better is the hydrogen generation. And these are with respect to all the standard couples, which are values known in the literature, and this is the scale with respect to the normal hydrogen electrode. So, this is a very useful guide when you want to choose a photocatalyst. Now, the subject of water splitting or photoelectrochemical splitting of water, which is one of the greatest challenges man has, because if we are able to split water, we have immense source of water on earth, even on other planets, then it will be very easy for us to generate hydrogen and oxygen. And if it is very easy to generate hydrogen and oxygen, we will have vast source of hydrogen. Vast source of hydrogen means vast source of energy, because hydrogen can be used as a fuel. So, tremendous amount of research and development is being tried in water splitting reactions, but we have had limited success so far globally in trying to get efficient water splitting reactions. And why is that? So, one of the reason is that the electronic structure of the semiconductor controls the reaction, and to modify the electronic structure without spoiling the semiconductor, without deterioration of the semiconductor is difficult. So, to improve the efficiency, you want to modify the electronic structure of the semiconductor, but while doing that you destroy its stability or some other parameters. That is one of the reasons. Then there are thermodynamic barriers to the reaction, like you have to have 1.23 volts to have water splitting. That gives little scope of improvement, because most of the materials where you can which can give you which have band gap of 1.23 volts have more or less been tried. So, totally new formulation have to be devised. All the known binaries etcetera people have tried. So, you have to find very new complex metal oxides maybe, or complex metal chalcogenides, which have band gap more than 1.23 volts, but have not been experimentally tried, or whose valence edge and conduction band edges have not yet been properly estimated. They can be tried. So, you have to think totally in a new way, and totally new compounds and formulations have to be devised. The third point why we have limited success is the charge transfer processes at the interface has to be understood, because if you want to design systems based on logic, then you have to understand the interface. Otherwise, most of the time you will be doing trial and error, and trial and error always takes long time. And charge transfer process has to be understood very well, because that is what will prevent recombination of the electrons and holes, and to improve the efficiency you have to stop the recombination of the electrons and holes. So, understanding the interface is very important for charge transfer processes. Then the increase is due to better light harvesting capacity of the dye sensitized nanocrystalline material. In dye sensitized cells, where we have added a dye, the increase in the efficiency of the electrochemical splitting of water can be due to or is due to better light harvesting capacity. That means, the dye is actually trying to act as a antenna and picks up this radiation much more efficiently, and that transforms the efficiency of the hydrogen and oxygen generation. So, that is one thing, but it is also due to the case we discussed of the film. It is also due to mesoscopic film texture, which favors photo generation and collection of charge carriers. The other thing is the nanocrystalline state in combination with sensitization together can be a worthwhile alternative. So, not only decreasing the size of the particles, but also using a photosensitizer, together they can lead to a highly efficient system. The efficiency that we have reached needs to be increased further, and challenges are lying ahead. This is an experimental setup for photocatalytic water splitting, and you see the core or the heart of the setup is the lamp. So, it can be a xenon lamp or a mercury lamp, and a mercury lamp is basically used for ultraviolet radiation. It produces ultraviolet radiation. So, you put the mercury lamp, connect it to the mains, and when the lamp glows, ultraviolet rays come out, and you have this solution with the nanoparticles or the semiconductor particles here, and then hydrogen and oxygen will be generated at the two electrodes. So, this is one of the lamps, and these you can also do similar thing with xenon lamp, and this has this GC is attached for analyzing the gases which come out. So, both the xenon lamp and the mercury lamp can be used. The xenon lamp gives out visible radiation. So, if your catalyst is visible light active, then you use a xenon lamp. If you are looking for UV radiation, then mercury lamp is fine. So, you can always use a higher energy lamp like a mercury lamp, but to see whether only visible region is active, then you need a xenon lamp to produce, because UV radiation will also promote create electrons and holes in a system where the band gap is in the visible, but visible radiation will not promote electrons and generate holes if the band gap is in the UV region. So, visible light will show you certainly that the band gap is in the visible region. So, why titanium dioxide has been used a lot, and we discussed, and that is because titanium dioxide is a green catalyst, it is non toxic. So, photocatalytic applications of titanium dioxide. So, in the presence of light, titanium dioxide has been used to deodorize your surfaces or any walls etcetera, by removing volatile organic compounds. The odor is basically caused by organic compounds which are volatile, which are in the atmosphere, and so the those organic compounds which are volatile are broken down by the photocatalytic reaction by TiO2, which in the presence of light acts as a photocatalyst. You can also purify air, because you can kill bacteria and germs in the presence of light, and TiO2 again acts as a photocatalyst. So, there are lots of these photocatalytic applications for deodorization, removal of odor, air purification, water purification, and sterilization. In all these reactions, there are tremendous applications of TiO2. Of course, TiO2 is a UV light photocatalyst. Now, you can have antimicrobial effect to remove viruses, bacteria, and in diseases. So, you can use TiO2 for all these antimicrobial coatings. So, all these examples of coating on the walls in hospitals and in offices or factories removes molds, spores from the air, or removes viruses, bacteria, etc. So, it shows an antimicrobial layer effect because of the photocatalytic properties of titania. Now, titania also shows self cleaning effect. So, these are examples. You see this is a mirror and this part of the mirror is coated with titania, and the moisture on this part of the mirror does not allow you to see clearly, but no moisture can settle on this due to the self cleaning effect of titania, which is also the hydrophobic effect of titania. Similarly, walls have been painted in several places with the photocatalyst, and they are self cleaning. In the presence of sunlight, the TiO2 becomes active and it removes dirts and pollutants attached to the wall and washes them away. After when it rains, this all those things which are attached to the wall will be washed away. So, it is self cleaning. In the presence of light, the catalysis occurs, and when you wash it with water or it rains, the walls become clean. So, hence these are called self cleaning effects and have been used on doors, door handles, windows and buildings, etc. So, TiO2 is an ideal photocatalyst, and that is why 36% of the research of the world, as shown in the pie chart, is done on TiO2. It is cheap, it has high photochemical corrosiveness, strong oxidizing power, and photocatalysis takes place at ambient temperature, and atmospheric oxygen is used for the reaction. The redox potential for photo generated hole is around 2.53 volts versus the standard hydrogen electrode, and after reaction with water, the holes will produce hydroxyl radicals. Both holes and hydroxyl radicals are more positive compared to ozone. So, if you see this oxidation potential, you see the hydroxy radical is much stronger than ozone as an oxidizing agent and much stronger than hydrogen peroxide. So, hydroxyl radical, which is produced by the holes in a photocatalytic process, is a powerful oxidizing agent as seen by the oxidation potential, and hence it will oxidize water into oxygen. So, several photocatalytic reactions are possible, and in the presence of light you generate electron and hole. The hole reacts with water to produce hydroxyl radicals, the electron reacts with oxygen to produce this dioxygen radical anion, and this radical anion reacts with protons to produce this radical. So, several of these reactions can happen in the presence of light and the photocatalyst titanium dioxide. Now, how does OH radical mineralize the pollutant? The OH radical reacts with organic compounds, which is the pollutant, and produces carbon dioxide and water. That is how it cleans your rivers which are full of pollutants by using titanium dioxide, etc. So, this is again in a nutshell to show you when light shines, electrons go one way and protons should go, the hole should go the other way, and the electrons on the surface can recombine, and the holes and the surface can go and oxidize, or they can also recombine. The electrons can recombine with holes, or they can go on the surface and reduce. You have to stop the electron hole recombination. So, this process and this process you want to stop to make an efficient photocatalyst, and the electron hole recombination is of the order of less than 30 picoseconds. Hence, efficiency is very low. So, this is the bottleneck. You want to stop the electron hole recombination, and you have only efficiency of around 5 to 6% in these water splitting reactions. So, finally, this is how the reaction looks when you are doing photocatalysis. So, this is the lamp which I was talking to you, a xenon lamp, a mercury lamp is placed inside, and solution is there with the photocatalyst, and electrodes are there, the electrode assembly, and you are doing photocatalytic reactions here. So, with that I come to the end of today's lecture, and we have one more lecture on photocatalysis. which we will be doing in the next lecture. Thank you.